Well, I guess we're live. It's a real pleasure and a real honor to introduce David Dunn to the Media Lab and to a Media Lab conversation. I'm Joe Paradiso, professor at the Media Lab, and I'm here with Gershon Dublon, one of our well-known alums here, who's worked in areas related to field recording and sound and music. And we've been talking for many years about having David sit with us and talk about his work and perspective. So this is for Gershon and I think for the whole lab, a very special moment. We're really happy that David could come out, at least zoom in with us in a conversation. So like many of us at the Media Lab, David wears a few hats. He's really well known as a composer working in areas where structure and sound can be driven or come from nature or nature-inspired processes. He presents sounds from the natural world in his pieces that humans normally can't hear, and or has us hear a natural landscape in an entirely new way that humans normally just wouldn't hear at all. So he works all ends of these spectrums. To do this, David develops his own transducers and his own recording production techniques. So he invents his technology as he goes. Again, very much in Media Lab style, and he's been doing it for a long time. He's had and is having an extremely productive life as an artist, composer, and acoustic environmental scientist. He started off way back working with Harry Partridge, I think as a teenager, performing with Harry's ensemble, and has also worked with notable people that are household names in this genre, like Paulino Oliveros and others that really are at the edge of music. So David has been there in terms of his mentors and collaborators, but also pulling off to do just amazing frontier work, really redefining how you hear things with his work continuously. He's won a slew of awards and commissions, and even in the current era when field recordings become front and center and common in electronic music circles, David isn't a past icon. He's still making compelling pieces that really turn your head around and make you hear the world in a fresh new way. So with that in mind, we're absolutely delighted to welcome to the Media Lab, David Dunn. So David, I think you'll start with a presentation, right? And then we'll go to Q&A afterward.
Yeah, I'm going to try to keep this really short. First, just thank you for having me, and it's really an honor to be here and to talk with you all. The presentation I just have kind of prepared in advance, some PowerPoint kind of things and a few sounds, mainly because I'm sure there are many of you who wonder who the hell is this old dude here that's going to talk, who have no idea what I've done in the past. But so I sort of prepared a few things that kind of locate that. Kind of chronologically, and I'll try to go through these really brief. Some of these have sounds, and I'll try to also keep it really short. Unfortunately, once you get me going, I'm a fairly introverted person, but I sort of can turn into a wind-up toy, so you sort of have to rein me in at some point. I'm hoping I can do this without being too effusive. So I'm going to start with just this one description. It's kind of a piece that is kind of emblematic of a lot of the earliest work that I was doing, which had to do with site-specific interactions using sound. It was very influenced at the time. Both of all my family, in fact, were visual artists. I was the kind of outlier who was interested in sound and music. And one of the things that really impressed me as a teenager was the land art where people like Robert Smithson and Michael Heiser, and I began to think about how sound might be used in a way that was even less intrusive, but had the same kind of aesthetic drive behind it of interaction with the non-human world. And some of these kinds of projects were large performance works or things that involved interaction in acoustic spaces outdoors. This is one of the pieces, which is collaboration with another musician, Rick Couples, who lives in San Diego. And we got interested in mockingbirds for the reason that they are so interesting in their ability to imitate sounds of the world. And since the time of doing this, there's been a lot of research as to what motivates mockingbirds and other mimidae birds to imitate sounds in nature. And one of the theories that's been advanced is that they're largely advertising, especially the males are advertising to potential mates the complexity of the biome where they live. And so they pick up sounds of other birds, they pick up sounds of other things. Where I was living at the time in San Diego, lived in a canyon that the other end of it ended at the San Diego Zoo, and I'd be awakened in the morning by the sounds of monkeys in my backyard. And it turned out to be the mockingbirds traveling up and down the canyon. And I heard them do like Volkswagen engines that needed a valve job, or bearings that were wearing out on a washing machine on someone's porch. And so the idea we had was, let's see if we could challenge the ability of the birds. So this is one of these really early, at that point, experiments in interspecies communication that was really driven by, to some extent, a sense of humor around what are these birds capable of. And so what you're going to hear, I'll just play a little bit of this. This is the birds is like 3 o'clock in the morning. We're playing back pre-recorded square waves, which were chosen because how hard they even are on audio systems. So what you're hearing is, initially, here's the bird, and it's doing its thing. It's a male, late at night. It's singing, trying to attract attention. And then you'll hear these electronic tones. So get the idea. You can just advance the slide. So, I mean, it was interesting because what we found was, without any prior exposure, these birds would just enter into this domain of interaction and imitation. And they were sort of like jazz musicians. We did a lot of different recordings and had a lot of different kinds of interactions. But the thing that was clear was that sometimes they'd be imitating pitch, they'd be imitating rhythmic patterns, they'd be other times doing other things. But it was always like a very, not a simplistic relationship of imitation, but one that seemed to be quite sophisticated. And that got me thinking about, well, what's the potential of this? It sort of led to a whole number of years developing technologies where I could do real-time sampling. At the time, there were samplers, but they were things confined, very large machines confined to studios. And I wanted to have something that has pretty sophisticated capability of looking at these things almost as linguistic properties, where I could invert, reverse, chop up, do things with the sounds in real time with insects and birds and other kinds of creatures. So this is just a picture of me. This is proof that aging does take place. And the machine that you're looking at is a 6502 SIM1 computer with custom wrapped memory. You'd had to download the operating system from an audio cassette machine every time you used it. Very primitive, but it was what was available at the time. But it's sort of, what's interesting is, of course, how now this is something you can do with multiple programs with an iPhone. In those days, and this is how fast the technologies have developed, of course. But at the time, I had to program this in assembly code, hexadecimal assembly code. It was a fairly heroic endeavor to try to get anything to work, and it was pretty unpredictable. You can advance the slides. We can go for it. Yeah. Look, and then a whole period of time actually experimenting with all kinds of different DIY transducer systems to amplify. Obviously, sound exists not just in air, but it exists in all sorts of vibratory substrates, in water and in surfaces and in soil and in trees. And so it's like a whole realm of experimentation. My criteria for experimentation was always, it has to be cheap, but as effective as the scientific equivalent. So something that might be an accelerometer that costs a couple $1,000s to do insect recording. How do I do that on the cheap? And it's mostly motivated out of just the realization I couldn't afford those kinds of tools. So how do you do it in a manner which is affordable for an artist in poverty? So the things had to be easy to make, something that probably easy enough which I've done many workshops building these things with kids who turn out to be, of course, the best field biologists imaginable. And we go out, we build these things and then spend days going out and doing things in the non-human world, recording all kinds of sounds and things. Many of these things they're sort of like a trip to Radio Shack and a trip to Home Depot, and then you can make them in a matter of a couple hours. Yeah, we can go on advanced slide. This is an example. Hydrophone, these have been around, homemade hydrophones have been around a long time. This just happens to be a tuna can. Has the advantage of you can have lunch out of the contents, and then you wash it out, glue piezo benders to the bottom of these, and then wire them up, and then a fast setting resin that sets up in a matter of minutes, and then paint it and wire it up, and you're good to go. It costs a couple bucks, plus you get lunch. Next one. Next slide. And this is a more sophisticated example of experiments, same kind of thing, but this is directional hydrophones, experiments using like double MS characteristics where you actually can have some rudimentary level of course, it depends on the nature of the sound. Something like a whale, usually you won't even get stereo separation with two hydrophones unless they're maybe 60 to 100 feet apart. But in this case, something like underwater things in ponds and lakes, these can be pretty effective at actually creating a stereo image. And example of that, next slide. This is a project that occupied me for a lot of years, going around the world and recording in freshwater ponds. It turned out there were these incredibly sophisticated sound producers, everything from caddisfly larvae to different amphibians, of course, but also this is a representative of what the Barosis genus of beetles, which are, they store their air supply under foliage. So you see them carrying air bubbles back and forth. It turns out they have this really very sophisticated communication system. And you find them in these ponds all over the world, along with a lot of other creatures. So we can just hear the sounds by advancing. There we go. Next slide. So I was at a conference a number of years ago in Prague, and doing a presentation with one of my colleagues, the physicist James Crutchfield. And at one point, one of the people in the audience asked, "Well, Mr. Dunn, what is your criteria for how you go about doing this kind of work, and how do you go about making these decisions?" Before I could say anything, Jim spoke up. He has a great sense of humor, and he said, "David has a very simple algorithm for success. He goes out and he sticks things where nobody has stuck them before." And this next transducer is a perfect example of that. This is an insertion microphone made out of a tiny little hearing aid capsule that's mounted in the end of this shaft. Then it's stuck down into the ground, into an ant nest. We can see the next slide. This is the ants you'll hear. These are Western harvester ants, which I had a giant mound of these in my backyard for years, which I just love to observe. They're so interesting as an insect. They're also one of the most venomous. They sting and bite, really painful. But I sort of put up with them because I was so fascinated with them, sort of this underground brain in my backyard to observe and to listen to. But let's go ahead and advance. This is about 4 feet down in the ground. And you see the back end of the very far end, the bulbous back end, which is called a gaster. Towards the connecting tissue in front of that, there's a sound producing organ. And that sound producing organ is a cat called a pars stridens. The surface of it has grooves that sort of look like a phonograph record. And then they have a little plectrum that rubs across the surface of that. It's like a percussion instrument. And they simply, that's not an ant. It just gives you an idea. This is 4 feet in the ground, how high the amplification is to pick up crows that were flying overhead. So they move that back and forth, and the tissue rubs, and it creates the stridulation that you hear. Next slide. And this is the application of the same little transducer. I started experimenting, trying to find small, cheap capsules that would have an ultrasonic range. It turned out these little Knowles hearing aid capsules were the perfect thing because they go up way high into ultrasonic range, but they do have a roll off. But what was interesting, I found when researching them, testing them, was that the noise floor, the self noise, rolled off at the same rate as the frequency response. So you could boost the high end and have still a really interesting recording, clear up to like 120 kilohertz. And as I was doing this, I was buying lots of these. And I got an email one day from a marketing person at the company saying, Mr. Dunn, what do you do with these? We usually have people buy one of these or they buy 1,000. Nobody buys 20 or 30. And we're just really curious what you're doing. So I explained that I'm using it for bioacoustic research. But 2 months later, I get an email of a product announcement from the company saying, with all this research they've done, basically verifying my, so I don't know, they could have at least given me some free capsules, but doing free R&D for them for a period of time. It turns out they're very effective. Here's a boundary microphone, traditional PZM boundary microphone that is very effective at giving you like a 6 dB increase in amplitude because of the reflection from the surface. Standard technique, but nobody had applied it to ultrasonic range. So these were really simple. This is just like an electrical plate cover with a little wood armature and the thing is mounted. So again, this is maybe a $40, by my terms, a very expensive transducer development, but compared to my other things that I do. So we can, yeah, let's advance. And this is an example of what this is used for. So this is near where I live in Santa Fe, a place called Diablo Canyon, has a very large population of Brazilian free-tail bats. And Brazilian free-tail bats are interesting because they not only use echolocation for hunting, for seeing in the dark, for sensing in the dark, but they also have near ultrasonic range songs that they sing. And that's just within the species, the communication. So they're quite beautiful. But so you'll hear, that's actually what you're going to hear if we advance the slide to hear the sound. This is an example not of their echolocation, but their communication amongst themselves. This is produced by dropping this about tenfold sample rate conversion. So it's not only dropping the frequency into a linear range, but stretching it commensurate amount. So the reality of these sounds is way higher frequency, but also very, very short compared to what we're doing. And some of these are effective for research purposes. Some of these transducers. This is a really simple one. This is a piezo bender with a little chunk of dowling, hardwood dowling, and an old gramophone needle mounted in the middle of it. And this is really effective at picking up things like leaf hoppers, tree hoppers, and suspend it. And in this case, I was doing some consulting work with the FDA, or the USDA, I'm sorry, the Department of Agriculture in Maryland. And we were looking at the sounds being produced by these tiny, tiny little ambrosia beetles that are about the size of a poppy seed, that are responsible for about 40% crop of the world's coffee crop. And usually it's only like one of these little beetles gets into the coffee fruit. And so I was the first time ever amplifying the sounds of these little creatures. Again, it's ridiculously inexpensive transducer for that purpose. Next slide. And that's what they look like. And this is one of the many kinds of bark and ambrosia beetles, about 7,500 documented species of these. It's a subgroup of weevils. And advanced slide. And this is another transducer that I came up with because of the effect on forest ecologies that bark beetles have. They're probably the second greatest change agent to forest ecologies worldwide, second only to humans. And they're very cryptic. They average about the size of a grain of rice. And about the time I started doing research around this, it turned out the trees, the pinyon forests here in New Mexico, where I live, were dying off in great numbers due to bark beetle infestation, which we now know is one of the major fuel sources for the wildfires throughout the Western United States. And a major contributor to issues, atmospheric issues in terms of climate change. This is a really wonderful little transducer. It's about these little meat thermometers you can get at Target and other places in the kitchen section that cost about $3 or $4. It's gutted, a plastic washer glued in, and a piezo mounted on top of that. They have a little spring for the thermometer part of them that's just pulled out. So again, it's about $10 to create this. And now I get requests from all over the world asking for my schematics on my transducer for bark beetle amplification. And of course, it's like totally embarrassing to respond to these requests. Next slide. And that's what they look like. This is a pinyon. This is a type that goes into, bark beetles tend to be either specialists or generalists. In the case of these, it's about the size of a grain of rice. They're incredibly, I think, beautiful creatures. And they infest trees massively. Next slide. And this is what they sound like. This is recorded with that insertion, that transducer is inserted actually through the outer bark into the phloem layer where they live. And we know how they produce sound. They again have a pars strident organ. Different species have it in different parts of their bodies. Same as like with the ant, they have a little plectrum that rubs across the surface of that and making these stridulation sounds. Next slide. Next slide. And this is, of course, their effect upon forest ecologies, which is massive. We've had just millions of hectares of forest throughout the West. now extending into Canada. Probably the largest insect infestation in the fossil record of Earth is what these creatures have managed to do, and it's largely due to climate change. Next slide. And some of these are also, these are ambrosia beetles. This is one that a new species that appeared in North America. It's the size of a sesame seed, and it goes into virtually every known species of tree. We had one of these probably appear 15 or so years ago, and I think it was in Long Beach, came in a shipping container from Vietnam, takes one fertilized female, and within a matter of months, you'll have like hundreds of millions of beetles in one tree. And they basically kill every tree they go into. They're now in every species of laurel, oak, fruit trees, nut trees, you name it, these little guys are in there. We have no idea what the implications of these are for the future. It certainly has already had a devastating effect on the avocado industry. It's an extraordinary little creature. Next. And here's an example, a couple slides just showing you the details. This is, of course, scanning electron microscope imagery, which I just got totally addicted to. It's like you walk into a lab where you do taking these things, you gold plate these little beetles, and then you scan around looking at them, and it's like, you emerge 2 months later, forgetting what has happened to the world. Next slide. And they're just fascinating. So this occupied me, this kind of research around bark and ambrosia beetles and their bioacoustics, because it had been a field of science largely forgotten about. It was sort of state of the art in as late as the 1970s, and chemical ecology took over the paradigm for this. And that's an absolute bottomless pit of potential what chemical ecology is, because we know that's the major way in which insects do communicate. But their second way they communicate is through sound. Next slide. And this is the kind of impact they can have. All of these creatures, all bark and ambrosia beetles, have a symbiotic relationship with various forms of fungus. Some farm it, some just carry it from tree to tree as the mechanism by which they can optimize their own population cycle by bringing the tree down. This is what actually kills the tree, is the fungus and not the beetles. Next slide. This is the lab where I was working at Northern Arizona University, because after I started revealing for the first time the actual sounds recorded in trees in the wild, a couple of researchers there, entomology forest researchers, contacted me, wanted to replicate what I was doing, and we began a series of experiments using sound to try to affect the behavior of the beetles. And what you see there is a set of chaotic oscillators, which I designed, circuits designed to produce autonomously, not constantly changing sounds that the beetles actually interpret as probably predation threats. And then we were doing various sampling techniques where we're playing back sounds they were familiar with, which seemed to ready them neurologically, and then bombard them with these other things. Next slide. And next slide. These are the circuits. But one thing I have to admit in my career is that what distinguishes myself as a researcher is that I seldom have any idea what I'm doing. So I sort of progress along intuitively and heuristically and end up teaching myself electronics with no real background in it. And so I got interested in these chaotic circuit systems, and because of their potential to have these complex, non-repeating things that the insects could not habituate. Next slide. And this is one of these major circuits. It's based on this particular ODE circuit implementation of that. I made some changes, so it has a very, very interesting, different chaotic attractor. And then multiples of these, which are all interacting. So a change in one of them causes a change in all the multiples of these things. So they start to cascade in extraordinary ways. And it's really interesting from a sound standpoint, but really annoying to bark beetles. Next slide. This is what they sound like. This is just turning the circuits on and they do their own thing. So if you're an electronic composer, this is really cool. But if you're a bark beetle, you can advance. Next slide. This is what happens to bark beetles. After about a week of exposure to this, they would actually try to tunnel out of these special systems we created. We call phloem sandwiches, which we lay the phloem layer, sort of like an ant farm, and we could observe their behavior in response to different kinds of sound stimuli. And this is an example of one beetle chewing through 1/4 inch plexiglass to escape the sound. So we actually managed to shut down their reproductive cycle completely and turn about 10% cannibalistic, and a large number of them would actually chew through the plexiglass to try to escape. So it was pretty effective. Next slide. And that led to a number of scientific publications around this. Next slide. And patent. We filed patent for this, achieved international patent actually, which we think may be effective in an agricultural context. It's like way beyond something that could probably be applied to a forest ecology for obvious reasons, just the level of scale that's necessary. Next slide. Next slide. And then there are these various microphone experiments that I've done. This is an example of an 8-channel one, which is ultrasonic, using those same kinds of little Knowles capsules with this ultrasonic range. Next slide. And this is an example of a Townsend big-eared bat at Pinnacles, the newest national park in California, where there's a very large colony of these. And using that particular microphone, next slide, so you can hear it. This is using the same sample rate conversion techniques. But what's really cool about these microphone arrays is that since they're multi-channel, I can actually record these in the flight patterns as a surround sound reproduction. Next slide. And a more recent version of this is actually a second-order ambisonic, ultrasonic octahedral microphone that I've been having a lot of fun with. Next slide. And here's an example of the kinds of things. Most of what motivates me in the kind of work I do is just being curious about things and trying to discover things. And this is the kind of thing that happens when you just go out and you do this without really just trying to record one thing. Things reveal themselves in the natural world. And this is an example of we think is an ultrasonic amphibian. This is in Mexico, and it's in the foothills of the Sierra Madre. And it was recording bats at night, and then heard this other sound, which we've been for a number of years trying to track down what the source is. We haven't been able to. Some kind of toad, some kind of amphibian, which is actually producing an ultrasonic signal. You'll hear after the sample rate conversion. There's only ever been maybe 3 or 4 ultrasonic amphibian species known. So it would be kind of really cool if we could track it down. Next slide. That's the bats. And that croak is that. So you just never know what you're going to find. Next slide. Next slide. And this is an example of the last kind of thing I'll just talk about, and then we can get on to some questions. This is looking at large spatial scale recording. How do you record very large locations at very high sample rates? Next slide. This is a place in the Santa Cruz Mountains. Next slide. It's about a half mile in diameter, and we use 6 different surround systems to record at a large spatial area. This is just a fanciful representation of what kinds of reflections and kinds of things that are occurring with multiple sources as a complete alternative to all the traditional rules of audio recording. It's violating most of them sort of intentionally. Next slide. And a playback configuration for this. Next slide. And this is just an impressionistic thing, this mapped into a binaural playback. What occurs with this kind of recording is you have these incredible distances between this, and I'm sure that some questions will arise. It's already been asked, so I won't say a whole lot and just respond to this in terms of questions. But the thing that occurs here is all of these incredible anomalies because of the delay due to the speed of sound at these great distances. So certain locations share sounds, others that's traveling and the delays are quite conspicuous. Sometimes they just sound like conventional reflections that would occur from natural surfaces, but actually, in fact, a lot of this is due to just simply the nature of time and the delays that we ordinarily in conventional recording try to compensate for. Next slide. And then advance that, and we'll hear just a little bit of this, and that'll be the end of this. Yeah, next slide. So what you're hearing is a binaural mix, which is sound that's inclusive of a central location mapped into binaural headphone space, but then the sounds that exist for a quarter mile to the left and a quarter mile to the right, all occurring simultaneously. And these are tourists walking the trail around this lake. What's interesting about it is it takes on a kind of symphonic property that ordinary location recording doesn't have, that characteristic. And of course, what it does is make apprehensible something that no set of human ears could actually have access to except through the mediation of technology. Okay, I think we can shut that down. So, I guess questions.
Thank you, David. This is just awesome for us to see and hear. We've long wondered how you recorded these things. We heard in your pieces how you use some of these pieces, but the stories behind them just fill in so many gaps, and it's such an amazing story. We had Rex Calcroft come to our class to give a lecture on recording things in plants, sounds in plants. He uses these expensive piezo accelerometers. You get so much distance out of a little piezo disc. It's just incredible how well that works.
Yeah, I actually showed some of these to Rex at one point, and his response was, "Why didn't I think of that?"
Yeah, we turned him on to the analog devices guys to make the cheap accelerometers. It could work for him, but you're going another level. And those discs, if you know how to use them, they're so effective.
Yeah, and really cheap.
I'll ask just one or two quick questions. Turn over to Gershon, then we have some questions coming from people. Time goes fast. In Horseshoe Lake, I'm listening to it a lot the last days, and I immerse myself in sound of light in the trees for a long time, and I've listened to some of your other things. We talked a little bit about this, but in Horseshoe Lake, you're in the audio band, it seems, but are using also hydrophones and other sounds you can hear and mixing them in together. And you have human sounds as well, right? It's not just nature, it's the space, it's the place, not so much just the natural processes. It's the whole thing you're bringing up to people. As an artist, when you're making this, are you crossfading and working on which microphones come up where, or is it just a segment at a time? You got your audio transformation, you just let it go?
It's just a segment of time. It's like everything that coexisted in these different multiple locations simultaneously. Mm-hmm. And the only thing that ties them together was the synchronization that was maintained by using simple, cheap radio microphone transmitters and receivers that are just transmitting time code.
Yep. You can hear a little bit of the slapback from the different delays. Oh, there could be, cliff surfaces too. It's coming together to give you a sense of a place. And it's a big place because of the spacing of the microphones. And Light in the Trees, you mentioned to me, you took sounds from different times and put it together. So there as a composer, you're also, are you just kind of, that's a whole day, I guess, right? Are you picking it, mixing it, and putting it together to do an arc of your choice, or you're somehow or other just letting it do what it does?
That piece was probably collected from I would say 50 different trees.
Yeah.
And the idea was that the underlying metaphor was, what would it be like if I could place hundreds of transducers into one tree where all these creatures are doing their thing at a local level? Yeah. So in this case of the tree, we are all pinyon, the kind of pinyon trees that exist here that this one particular species goes into. And so it was how to select, how to mix, and basically using, an education as a composer for the criteria of that, but being driven by an assumption that I'm really standing in place, though. I'm being the representative of this natural phenomenon. So I'm trying to weave it together in a way that gives voice to something that is another, that it isn't just about aesthetic criteria. It's about how can I help to reveal and optimize the sense of what the living thing is that I'm looking at or listening to.
Yep. And in the natural passage of time that you more or less compress there.
Right.
Yeah. With your bat stuff, it's just so hauntingly beautiful to hear that sound. And it's again a sound people don't normally hear. We have bat detectors, but those just mix it down, so it's not a harmonic pitch shift, right? You're doing the right time compression to save the harmonics, and it makes a huge difference. Are those artifacts you hear periodically actually different kinds of calls the bat makes, or is it just in the algorithm?
It's all just what the bats are doing, but because of the sample rate conversion to drop it down into our hearing range, there are all sorts of artifacts, or at least appear to be artifacts, just because we're dealing with something that is at a time scale that's infinitesimal to our perception, stretched out in time. So there's all these very, very complex things. Bats have probably one of the most sophisticated neural systems on the planet. Just amazing what they're capable of.
It's incredible. And again, something can happen so briefly. It sounds like a glitch there, but it's in reality important to the bat. It's not a glitch. Exactly. Yeah. One last simple question. I'll turn it over to Gershon. I love the sound of the ant. I mean, that's definitely a sound coming from another species altogether. Is that only one ant? Because you would think if you've got a mound, you've got lots of ants. Did you have to put it really close to one and you hear one? It's like going to a neuron in the brain, you don't hear the rest? Or can you hear all of them?
What you were hearing just in that excerpt was one ant. Mm-hmm. But in the recording that was made, later on, you do hear other ants.
Yep.
And it's because of how the transducer is extended down into these tunnels, threaded down into these tunnels. These kinds of terrestrial ants are very responsive to anything. Obviously, a lot of that was probably alarm warning call.
And threat, yeah.
It was like, what is this thing in my world?
Yeah.
Ants are incredible for the sound production capability. One of the theories, at least that was posed by, I think it was E.O. Wilson, who proposed the theory that they primarily, again, are communicating through chemical signaling. And some species of ants have as many as 9 different little ports that they emit different chemicals. These different chemicals have different meanings. But in a closed system like a tunnel, all that stuff is going to mix. So one of the theories is that the sound stridulation is actually there to help not only as an additional form of communication, but it's actually modulating the clouds of the chemicals, binding them in particular ways through sound.
So it's contextual, but it has a chemical identity as well. Incredible.
Exactly. Yeah.
Gershon, time passes. Let's turn over to you. Go ahead.
Thanks, Joe. Thanks, David. This is just so amazing to have you here with us finally. So I had two kind of main question topics. And the first one was regarding time. And I guess that one is a good segue from what we were just talking about. In what you called the kind of symphonic characteristics of the final piece you played, I recognize that across a lot of your work, this kind of sense of you close your eyes and suddenly you are inside of the tree or inside of this forest in this instant. It's very transporting to the instant. I'm curious what you think about long-term or representation of long terms or longer cycles in your work, because you mentioned, for example, climate change or fires or kind of the effects of the beetles incursion over time. And this is a challenge that we face a lot in our work, in our recording and creative work, is just how to represent change. It's something that's very foreign to humans to think about change over a lifetime or change over even a decade or even a year. Do you think about that? Does that ever frustrate you as much as it frustrates us?
Well, I'm often dealing with phenomena at the small scale of things like invertebrates, where we're talking about a scale of change that we have virtually no concept of. It's one of the things that both in terms of large amount of time and very small units of time, the sub-ecology, the microecology that exists of, like, in the world of bark beetles and their relationship to fungus, there are so many factors that virtually every form of parasitism and commensalism and all these different biological, metabolic things that are going on can occur in a single tree, dramatically change literally from hour to hour at a microecological scale. It's something that we just don't have any sense of perception of. And at the other level of that scale, the kind of research that's now being done in terms of what's being called plant intelligence, the assertion from a lot of people studying this is that almost every criteria we've ever used to define animal intelligence exists also in plants. It just occurs at a time scale that we are completely unaware of. It's very, very long, the kinds of tropisms and the kinds of ways in which they're responding to stimuli exhibit all the same characteristics, but at a scale that we just, I mean, it's like, we live out our lives sometimes in the period that they're taking to have major change. So time, it's the thing that we, I mean, most physicists will say it's like, it's an illusion. Einstein said it's an illusion. It's like the arrow of time. Is something that we just can't seem to extricate ourselves from, but at the level of the symmetry of physical events in nature, it doesn't really exist to a physicist. Yeah, I mean, it's how to depict that, how to deal with it. It's a real problem because we're just, we are engineered to deal with a very narrow range of things within the electromagnetic spectrum. Our senses are what they are, and that's true of every living thing. The challenge always is, how do we wrap our heads around how another living thing is wired? It's, they're wired to deal with, I mean, most mammals and other animals, birds and amphibia, the relationship to sound is often defined by what it is that eats them and what it is that they eat. These are the responsive things that we're making to our environment. And that's true of us also. We have very severe limitations on what we're capable of actually sensing. And if you get into the domain of something like theories of self-organization, autopoiesis, like among the Chilean, like of Varela and Maturana, their assertion would be that was that our sensory mechanisms are extremely impoverished, and that most of our wiring actually goes from the brain to the senses rather than from the sense, our transducer mechanisms to the brain. There's more wiring going, which means that most of our experience of the world is being determined by our own individual history and our own individual experience. And it probably needs to be that way. Otherwise, we'd probably be completely overwhelmed So Francisco Varela once said that information is not something that we receive from the environment. It's something we project onto it. So that's the challenge we're always facing. So, I don't have a good answer to that other than it's a challenge and it always will be.
Yeah, that makes sense. Yeah, I see it as I voice it as a frustration, but I think it is kind of always been our goal, our challenge, that we're butting our heads against this as we do these recordings.
And part of the reason for doing that kind of recording, where I'm making purposeful the problematic aspects of our perception by these natures of these delays, is to bring that to the foreground. It's like, this is the reality. This is the reality. We can't sense things this way because it's the relativistic nature of time and space. We will always be in a narrow bubble of perception. And that's one of the things that's wonderful about both the advantage and disadvantages and confusions that the technology presents us with.
Joe, do I have time for one more question before we turn it over to the audience?
Yeah, of course, Gershon, go ahead.
Okay, so then my second question was really about your personal relationship to the raw recordings. I understand that you work as a composer, which means that you have, of course, a personal relationship to the materials that we hear on your albums. But the raw materials, I assume there's much more of the raw material that we don't hear. As the compositions being a collage or kind of a cutting down. And I wonder, as we move into a world where more people are posting materials online that they've recorded, the corpus of recorded material of the world is growing. Do you ever feel like you could sample that material, much like, I don't know, hip hop artists sample, or that material being personal to you is important to you as a composer? And I also ask this from the perspective of you as the designer of the transducer in itself. So no one will ever have the sound that you have, because the transducer is handmade and hand designed, really tuned to your environment. Do you have any thoughts on that?
Well, it's an interesting question, the standpoint of the limitations of technology, but also the limitations of exposure that people have. The advantage I have in making really cheap transducer systems is that no one has anything to compare it to. Whereas a very refined, high resolution, high sample rate nature recording in a forest ecology or similar environment, it's like the difference between, you go and record a string quartet, the thousands of string quartet recordings that exist are a comparison by which we are constantly making. It's why super expensive vintage microphones in recording studios are so valuable. It's because we're so trained to the cultural heritage that the sound of the transducer of the mechanism has, and we're always, whether we're conscious of it or not, we're comparing all of those recordings we've heard with each recording we hear. In the case of these transducer systems that I make, nobody's ever heard these things before. So I'm presenting something that there's no equivalent. There's nothing else. Oftentimes that's what I'm going for, is to reveal something that no one knows even has existed. And it's a great deal of fun, but it's also a real advantage in that I can present these things, and until somebody else starts going out. But the nature of the natural world is, again, so rich, so deep, so complex, that you could record any of these phenomena a myriad numbers of ways, and you're always going to come up with something really different, and no one's going to have anything to compare it against. So that's an advantage. It's an advantage. The cheap solution it benefits from the fact of this lack of exposure or ignorance about the nature of the phenomena that's revealed. I don't know if that answers the question, but that's kind of the reality that I'm dealing with. So the other aspect of this is that I think we're always bringing aesthetic considerations to bear. It's the nature, most of that goes unconscious. It's like just like the nature of people wanting to reject or accept or appreciate certain kinds of music. You know, music is an odd one compared to something like literature. You know, I've said this to classes I've taught where the reaction to an experimental music piece is, you know, ugh, God, that's such ugly sounds. I don't want to hear that. Or it's like, you know, just, I want to listen to my favorite band. Nobody, if you're in a literature class and somebody given the thing of reading War and Peace, nobody in the class hopefully is stupid enough to basically just respond when they're asked, what did you think? To say, I don't like it. But that's the kind of response we get with music all the time. And there's almost like there's a conspiracy I think for good reasons, for valid reasons, that we don't want to talk about music all that much. It's like something we want to like keep as a special case. And so our aesthetic biases are seldom brought into question, but we all have them. And part of what we have to do is also get past that, transcend. What do we do to transcend our own aesthetic bias around the nature of the things we engage with? It's hard to do, but it's really valuable to do so.
Here entirely. Is somebody who spends a lot of his life talking about music. I mean, you're so right. It leads to some doors that are closed, but if you give people the right perspective, it can open new ones and lead to a real transition too. It's wonderful to see people's eyes open when they can with new music. Not much time. We've already answered, I think, a lot of the questions in the chat. There's one that of course, is a great one. What's your favorite sound that you've captured?
Oh my God, that's really a hard thing. It's really hard because part of how I proceed with this is to not. I'm trying always to transcend that, and I recognize myself as a composer and as a musician, as, you know, somebody who does this kind of work. I'm kind of an auditory X-man, you know. I mean, I really am drawn to extremely gnarly, complex sound structures. Mm-hmm. It's like, what's my favorite? It's probably the next one that I encounter. I'm addicted to a kind of novelty of complex sound. And part of why I even originally designed those oscillator systems wasn't for I applied that to the bark beetle stuff, but it was really because I wanted to build a system that constantly revealed to me novel structures and that I didn't have to be responsible for generating them. The system would.
I relate with that, and always the next sound is the best one. we have a lot to live for. I would ask you, there's no time, but I would ask you what sound do you want to record that you haven't yet? And of course, now we can record sounds on other planets, right? We have the sound of the wind on Mars, something of Titan, although soon we're going to go underneath the ice and other oceans, and they got to have hydrophones because if there's something alive, it's going to sing. So let's hope we see this in our lifetimes. It's going to be incredible scientifically and as artists. I think there's a whole opportunity there too.
Oh, absolutely. Yeah, I mean, I want to hear the sound of things that won't propagate as sound.
Yeah.
The phenomena that exist, you know, I mean, my God, what a huge universe.
Yep.
There's stuff out there we have just
so much
to build the mechanisms by which we can engage with it at that level.
Yep. And even going ambisonic with multiple probes into your bark beetles or into an ant mound to do what you did with Horseshoe Lake with a tree. I mean, there are so many places you can go. And we're looking forward to that ride, David. So we'll be there with you. So thank you so much for coming to the Media Lab.
Well, thank you for asking me. I really very appreciative of what you guys do. And it's really an honor to.
The honor works both ways. It's been wonderful. So thank you very much. I guess they pulled the plug here.